with this given information, I want to be able to solve equations. But before I do that, I want to show you one neat trick, just in case you ever go into a higher math. This trick comes in handy. And the trick is this. You can change any exponential function into a base of e. Technically, you can change it to any base that you want, but the one that higher mathematics wants is a base of e. So, for instance, if you have a function and it's 3 to the x, and you don't want to deal with the function of 3 to the x, you'd rather deal with the function e to something. Well, it's actually kind of easy to do. The first thing you do is you write it as 3 to the x is equal to y. And you apply, let's see if I want to do it this way. What you're trying to find, I'm sorry. I got this messed up already. I'll cross this out. It's not horribly messed up. 3 to the x is equal to e to the y. And what we're trying to do is we're trying to solve for y. Because if we can find that power of y where this equation balanced, then we have converted 3 to the x to a base e function. So what would be your first step of solving this equation? What do you think? If you're going to try to solve for y. A couple techniques you could use. Number one, you could try writing it as an exponential back to a logarithm. It gets a little confusing there because they're both exponentials. So the other trick is use the inverse property. What's the inverse of e to the y? Because we want to get the y by itself. Well, e to the y's inverse property is log base e. Log base e. And log base e is also known as ln. Remember I was lazy last week and I said ln is better because it's only 2 letters rather than 3. So ln has a base of e. So what you could do to this equation is you can apply that function to both sides. Here's 3 to the x, here's e to the y. And you apply this ln function to both sides. Now the cool thing happens when ln and e are right next to each other. Same thing will happen if log and 10 are right next to each other. Because remember, log is base 10, just plain old log. When ln and e run into each other, they kind of cancel each other out. I usually say the word poof. And when they go poof, what's left over is just the variable that's there, the y. So on this side, you get y. Over here, we can use a law of logarithms. If you have a log of something raised to the power, what can you do with the power? If you have a log of something to the power, you can take the power and put it right in the beginning. So this x that's up here can now go out front, and you get x ln of 3. Thus, in essence, solving for y. And that's a lot of what we're going to do today, is solve for a single variable in these weird equations. So what we can do now is say, well, f of x is equal to e to the y, but y in this case is x ln of 3. And those two functions look identical to one another if you graph them. 3 to the x and e to the x ln of 3. So that's just a neat little trick in case you go any higher. What we're going to do today is solve a lot of equations. So this is 4-4. And 4-4 requires a lot of those little tricks of laws of logarithms, converting exponentials into logs and vice versa, inverse properties. That's about it for solving equations. And one other one. something from 2 chapters ago, functions. When you're dealing with invertible functions, functions that actually have inverses, they had a special name. Do you remember what the name of them was? If you could find a function's inverse, it must have been something first. No one remembers. 1 to 1. Remember 1 to 1? Small, tiny bit of brain. Someplace. So, both log and exponentials are 1 to 1 because they're inverses of one another, therefore they must be 1 to 1. Or you can go back to their graph and perform the horizontal line test. And if the graph only gets hit once, and if you look back at these graphs, a horizontal line is only going to hit them once no matter what. And the special property of 1 to 1 functions is this. If f of a is equal to f of b, then it must be true that a is the same as b. This is a special property of 1 to 1 functions. If their y values are equal to each other, their x values have to be equal to each other. And that allows us to solve these type of equations. 4 to the 2x minus 3 is equal to 8 to the x plus 4. Get that over. So if these two exponential functions are 1 to 1, if I can force them to be the exact same base exponential functions, then their x values have to be, or their domain parts of their functions have to be equal. So what number can I force both of these bases to be? 4 and 8. What's another way of writing 4, product-wise? 2 times 2, better known as 2 squared. So I can replace the 4 with 2 squared, raised to the 2x minus 3. What can I replace 8 with? Well, what's 8 factor into? 2 times 4, but 4 is 2 times 2, so how many 2's is that? 3. So that would be 2 cubed is the same thing as 8, raised to the x plus 4. Alright. What happens when you have a base raised to a power, raised to another power? In other words, power to a power. What do? Multiply. So this 2 is going to distribute over that power. So we're going to get base 2 raised to the 4x minus 6 is equal to, on the other side, you're going to distribute the 3, because power to a power here also multiply. You're going to get a base of 2, 3 times x, plus 3 times 4. And this 4x minus 6 and the 3x plus 12, those are exponents, those are powers, they're not down below. Now by the 1 to 1 property, they're exactly the same function, base 2 functions, therefore their powers must also be equal. Think of it this way. If I have 2 to the a is equal to 2 to the b, this law says that a has to equal b. Their domain parts have to equal each other. So it's not that the 2's are canceling. There's no canceling going on here. It's just recognition that, remember what the 3 dots mean? Therefore, their domains must be equal. 4x minus 6 must equal 3x plus 12. So it's not that the 2's are just disappearing. We're just saying we know the y values are equal, therefore the x values have to be equal. All right, how do you solve this nice linear equation? Did the test take all the brains out of your brains? All the cells are dripping out your ears. Oh, your linear equation. How do you solve it? Move the 3x over and you get x minus 6 is equal to 12. Therefore, x must equal 18. So if I plug in 18 into the beginning of this problem, these two things would equal each other, rather large numbers, if I would say so. 18 times 2, 36 minus 3. So that'd be 4 to the 30, 30. I don't think your calculator would appreciate that. I don't think you'll actually do it very nicely. But it's solved. I mean, you get down to x equals 18. And that's pretty much how it works. Logarithms do the same thing because they're one-to-one functions. For example, if you have log base 5 of x squared minus 6 is equal to log base 5 of 5x. Now this trick only works if it's one term on one side and one term on the other side, and both of them are exactly the same functions. Kind of like over here, we had to force both of the functions to be base 2. These are log base 5 functions, so you can't have log base 5 on one side and ln on the other side. That's not going to work really well. So as long as the functions are exactly the same and they're equal to each other, then what we can say is right away, this one's quicker than that one, right away the insides must be equal to each other. So the domains must be equal to each other. Now once you get this far, it's just, solve that equation. How do you solve this equation? Number one, what kind of equation is it? Quadratic. I love these whispering people. How do I solve a quadratic equation? What's the guaranteed one step? First step, at least. What? Get it equal to 0. Yeah, definitely. So move the 5x over. So you get x squared minus 5x minus 6 is equal to 0. Next step. Factor it. Factors of 6 that subtract up to 5. 2 and 3 add up to 5. 6 and 1. So this is going to be the 6th 1 break. So you get x of 6, x of 1. What kind of 6, what kind of 1? Negative 6 and positive 1. So when you take the two factors and you set them equal to 0, you're going to get x is equal to 6 and x is equal to negative 1. Okay, and most people are like, oh, there's our answers, we're done, and go on to the next problem. There's a slight problem with logarithms that exponentials don't have. When you solve an exponential function, the domain of an exponential function goes all the way to the left, all the way to the right, negative infinity to positive infinity. Logarithms, on the other hand, you got to be very cautious with. Their domains is not negative infinity to positive infinity. They start at 0, and then they go to positive infinity. So if you have a logarithm, you cannot, excuse me, you cannot take the logarithm of a negative number. Try it on your calculator sometimes. Take the log of negative 2 and see what happens. Most calculators will come up with domain error. It'll pretty much say that you're on the wrong side of the domain. So when we're dealing with logarithms, they only work on positive numbers. So log of positive is the only thing you can take. You cannot take the log of 0. You cannot take the log of negative numbers. The only thing you can do is a log of a positive number. So if I take 6 and plug it back in, I'd better give me positive answers on the insides here. So over here you get 36 minus 6 is 30, so log of 30. Over here you get 5 times 6 is 30, log of 30. That's perfectly safe. The one I'm worried about is at negative 1. If I plug it into the first one, it gives me log of negative 5. And right away you can't do that because you can only do log of positives. So this answer is what's called erroneous. You generate it, but it doesn't exist. We've done that before. Rational expressions come up with an answer that when you plug it into the bottom, it becomes 0 and you can't use it. Same thing here. So the only solution to this one is x equals 6. All right. Harder. I'll just look at my notes. I didn't bring my notes for that one. Find a harder one. If you have something like this, let's make it base 2. So this doesn't work the same as this one. This is log equals log. This is log plus another log is equal to a constant. Doesn't even have a log involved with it. So what kind of trick can we pull here? Well, we can do what's called a contraction. Where do you think a plus comes from between two logarithms? What was it originally? By the laws of logarithms? I'll write it down. Log of m times n is equal to log of the first one plus log of the second one. So here we have log of the first one plus log of the second one, so I can take it and write it as a single log of a product. So I can take these two and bring it together as a single log, write it once, log base 2, of what? The first one times the second one. What's the first one? X plus 1. What's the second one? X plus 3. And this whole thing is equal to 1. That's forcing the things to come together under a law of logarithms. Second thing we can do now. This is a logarithm of something very ugly is equal to a constant. Well, I can't work with it as a log anymore. So if you can't work with it as a log, what can we change it into? Well, all logarithms can be converted into exponentials. So if I'm going to convert this into an exponential, what's the base? Is it 1? No. It's on the other side of the equation. Is it the two products? No. The only base here is 2. It's read log base 2. So the first thing you write is the base. The power is the answer to a logarithm, so the power is 1. And it's equal to what's inside. And now it looks a little better. The logarithm is gone. No exponentials are really left over because 2 to the first is just plain old 2. What kind of equation is this? Eventually. It's another quadratic. So this side is just 2. X plus 1 times x plus 3 is x squared plus 4x plus 3. Then what? How do you solve a quadratic? Move the 2 over, get it equal to 0. So you get 0 is equal to x squared plus 4x plus 1. Ah, darn it. Are there factors of 1 that add up to 3 or 4? How do you want to solve it? Oh, boring. Complete the square. Why? The middle number is even. It makes life a lot easier if you complete the square. So write it as x squared plus 4x, leave a space, equals -1. It'll save you tons of time if you do it on the ones that are lead coefficient of 1, even number in the middle. Half of 4, square it. If you add 4 to the left, you better add 4 to the right. The left-hand side is a perfect square, the right-hand side is just 3. What perfect square? X plus 2. It's that half number. And then you square root both sides. And you subtract 2. Ooh, ugly answer. Analysis. There's two answers here. -2 minus the square root of 3, -2 plus the square root of 3. What's true about both of the answers? If you have to use your calculator, please be my guest. What's the square root of 4? 2. So the square root of 3 is less than the square root of 4. So the square root of 3 is less than 2. Then -2 minus something less than 2 is going to be negative. And -2 plus something less than 2 is also going to be negative. And if I plug them in here, well, it might work. Hold on. I need decimals. I need a calculator. Come on, someone start pushing buttons. I know the first one's negative, so he's gone. Because he's going to be bigger than -3, and it won't work in the first term. But I'm not sure how small that second one is. 0.26? That'll leave this one positive and leave this one positive, so that'll work. -0.26. So our only solution is -0.26. Because 1 plus it and 3 plus it, those are both positive numbers. Kind of weird. Oops. Alright, those two are semi-common, or those three I should say. The most popular, though, are ones that are like this. Remember this formula? You learned it in 8th grade, and you learned it last week. It's the compound interest formula that tells you how much money is in an account if you put P dollars away for T years and a certain interest rate R. So let's say I have, at the end of the day, $2,500. Okay. Let's say I started with $1,000. And the interest rate is 5%, compounded monthly, so you get a 12 there, a 12 here, and T. This is of usually more interest to people. If I put something away, when will it get to be this amount? This is pretty much how my parents bought everything in our house. We had a tube TV. Does anybody remember? Older folks will remember tube TVs. My dad would fix it, and I'd play with the little tubes as missiles. And we had one of those when everybody else had solid state. We had one of those when everybody else had cable. We didn't have cable forever. They got it after I left. We had a couch that my dad would keep attaching straps to until they could afford to buy a new one. Nowadays, everybody goes out and gets a loan. Yeah. Problem with loans is you're paying banks interest, and if you save up money, then you're paying yourself interest, and you usually can buy things a lot cheaper than if you just get a loan out. So this one is saying, if I start with $1,000, how long will it take until it becomes $2,500? So I want to solve for t. The problem with t is it's up in the exponential position. So what is the first thing that we can do to kind of get t a little bit more by itself? Don't think too complex about this. You're not even looking at the t now. You're looking at stuff that's in front of it. What's the first thing I can move? Can I touch the 1 that's in the inside? No, because it's on the inside. So everything in between the parentheses, out of bounds. So what's the only thing I can touch? The 1,000. What can I do with it? Divide it across. So divide both sides by 1,000. That frees up a few things. 2,500 divided by 1,000, was it 2.5? No. Yeah, 2.5. 2.5 is equal to. Now, 1 plus 0.05 divided by 12. I can do this calculation. I just can't do anything with it. What is 1 plus 0.05 divided by 12? You don't see a calculator in my hand, do you?
Well, what'd you say?
1 plus 0.05. Oh my God, you've never calculated. Oh, what is it?
I did have that time too.
What is it? Just the 1 plus 0.05 divided by 12. Don't even touch that power part.
0.0875.
0.0875? Or
I
1.0875?
Oh, you said.
Yeah, 1 plus 0.0. 1.0.
Just rounded them.
0.04. You can't. If you round it to 1, there's nothing there. 1 to any power is just 1. So 1.004.
There's some other stuff.
Yes, I want the other stuff.
1, 6, 6, 6, 6, 7.
Oh, well then. We'll put a bar on it.
I ate a bar.
Raised to the 12t. It's a repeating 6. All right, now here's my problem. I have a number raised to a power. What's the base in this expression, this equation? Yeah, that 1.0044. So how am I going to bring the exponent down so that I can work with it? Because I can't work with it up high. I need it down as a normal algebraic variable. So what thing can I use to bring it down? No whispers today? Look at those properties of logarithms. Anything bring a power down?
You bring it in front of the 2.5. No.
I can't bring anything in front of the 2.5, no matter what I do. There's a property that actually takes a power and brings it down out front. You don't see it? I wrote it on the board, amongst all that other junk. You'd be lazy and make me write it? Log of m raised to a power is equal to a power times log of m. A logarithm will you can yank a power and put it in front of it. It's number 5 in the properties of logarithms. Number 5. It's actually the third property, but I put 2 others ahead of it. Remember the first thing I wrote on the board? So sad. And I did this earlier when we changed a base into an exponential with base e earlier. That was my first example. So anytime you have a log of something raised to a power, I can take the power and bring it out front. The problem is, this problem doesn't have a logarithm anywhere. So what I'm going to do is introduce it. If I'm going to introduce it, I have to apply it to both sides. So this is 2.5, this is 1.00417, we'll round it, raised to the 12t. And we're going to log both sides. Just plain old log. What base is log? Base 10. If it's not written, it's base 10. If I write base 10, that's fine, but if it's not written, it's automatically base 10. So on this side, you get log of 2.5. You can't change that. Log of 2.5. Log 2.5. On the other side, the law of logarithm says I can take that power and drop it right in front. Just drop it as a normal, everyday kind of variable. So it becomes 12 times t times log of 1.00417. Get that ugly mess. What are we trying to solve for after you get that ugly mess? T. Now the t is buried right here. How do I get the t by itself? You can divide by 12. That's one of the things you have to divide by. So that would remove part of it. What else can you divide by? Everything but the t. So you divide by 12 and you divide by log of that mess. Now log of that mess is just a number. Your calculator can figure it out. It's just a number. So getting t by itself, I would divide by the 2 other pieces that are next to it. So divide by 12 log of 1.00417. And that'll cancel out both of those numbers, and t will be by itself. And divide the other side by 12 log of 1.00417. Now be really careful with your calculators. This long fraction bar here, remember from way back when, first day of the semester, long fraction bars are the same thing as parentheses. And you need those black parentheses around the bottom. Otherwise, your calculator is going to spit out the wrong answer. So type that in your calculator. Use the LOG button on it. And see how long this thing is going to take. T is approximately. I'll pull out my calculator. Log 2.5. Don't forget to close the parentheses after that 2.5. Divided by parentheses 12 log 1.00 417. Ooh. Oh. How long?
Which one? How long?
How long?
How long?
What's your answer?
I got like 18.
18.34? 35? Yeah. You got it? 18?
No, I didn't get that. How did you get that?
When you type it in, you have to type in LOG. When you do that, it'll put the first parentheses. You have to put the 2.5. You have to put the last parentheses after the 2.5.
Okay.
Then divide by parentheses 12 times log of whatever. The last one, it shouldn't cause you any problems. That first one, you have to be really careful with. And you should be getting about 18.3, give or take a little bit. Now this is 18.3 years. Take 78 out of the book. Log 2x minus 1 equals log x plus 3 plus log of 3. This would be out of 4,4. Solving a logarithmic equation. Now, the two main ones that I showed you on Monday were the same base exponential functions where you force them to be the same bases and then let their exponents equal each other using the one-to-one property. And if it was a log equal to a log, we could also use the one-to-one property. That's the way I'm going to lean for this one. But it's not log equal a single log, it's a log equal two separate logs. So what I need to do is take the right-hand side and condense it as a single log. So when you see a log plus a log, what operation really exists between the factors? Multiply. So I'm going to rewrite this as log of 2x minus 1 is equal to log of the product 3 times x plus 3. And that way I get log equals log. Once I get to log equals log, what must be true about the inside stuff? The y values are equal to each other in a one-to-one function, so are the x values, yeah. If you have log of a is equal to the log of whatever b is, then this implies directly that a has to equal b. There's no other way about it. They have to be the same domain value. So then basically what you can do is you can drop the logarithms. It's not canceling them. You're not going through and crossing them off or dividing them through because you can't divide by a function. You're just recognizing that 2x minus 1 has to equal 3x plus 9 after distributing that 3. And then solve this nice simple linear equation and you're done. Move the x over, 2x over, subtract 9, and you get x equals negative 10. Now, next part of the question. Can x equal negative 10? I did get the sign right? Subtract 9, negative 10. Can x equal negative 10? Well, check your answer. Log of negative 20 minus 1, better known as the log of negative 21. What's wrong with this? Oh, you typed it in your calculator. How sad. Oh, that's because you weren't here Monday. Why can't I have log of a negative number? I said something really specific. You can only take the log of positive numbers. So, if you remember anything about the graph looks like this. Crawls up the y-axis and shoots off in that direction. It never takes on negative values of x. It only works with positive values of x. So this is undefined, Therefore, this is not an answer, and the only answer to this is there is none. There is no solution to this problem. So you have to be a little bit careful of logarithmic equations. You have to check your answers back into the problem. If it gives you a log of a negative number, you can't use it as an answer. It's like dividing by 0. You just can't do it. It has to be log of positive numbers. I forgot an example. Oh well. We'll come back to it near the end. How about this one? A little more practice on these equations. Where is it? 1/4 raised to the negative 2x minus 5 is equal to 1/8 raised to the 3x plus 4. Another one-to-one property. Logs are nice because once you see log base whatever, you can compare them and say they're the exact same function. Exponentials can get a little different because the bases don't necessarily have to be exactly the same, and sometimes you have to kind of force the issue. So what's another way of writing 1/4 and 1/8 so that they have the same base? Think of it as a number raised to a power equals a fourth. A number raised to a power equals an eighth. So what number raised to some power is equal to a fourth? 2 raised to what? 2 squared is 4 though, not 1/4. Negative 2 squared. Negative 2 squared is like positive 4, and you don't want a negative base anyway, so you want to stay away from negative bases.
So what would it be 2 squared?
2 squared is 4. This is 1/4. What times what is equal to a quarter? What times what is equal to a quarter? 5 times 5 is 25.
That's a quarter.
Half. A half of a half is a quarter. So I can write this side as 1/2 squared raised to the negative 2x minus 5. Probably didn't need those parentheses, but I like putting them. Have it, I guess. All right, what about 1/8?
Same thing. 1/2 cubed.
1/2 cubed. So this 1/8 is 1/2 cubed raised to the 3x plus 4. Now there is another answer. You could have also said 2 to the negative 2 and 2 to the negative 3. 2 to the negative 2 is the same thing as 1/2 squared, which is the same thing as 1/4. 2 to the negative 3 is the same thing as 1/8 2 cubed, which is 1/8.
But that's what I said.
Oh, see, I thought you meant this is a negative
that's
2.
what
I was
said.
asking for the base.
Okay.
To what power?
I was,
The base. Oh, well, you are ahead of me then. All right, here you get power to a power and you multiply, so you get 1/2 raised to what power? When you have a base raised to an exponent, raised to another exponent, what do you do with the 2 exponents? Multiply. So you go 2 times negative 2x is negative 4x. 2 times negative 5 is negative 10 equals. Power to a power, you multiply. All right. On the other side, it's a number raised to a power again. So you get 3 times 3x plus 4, and you get 1/2 raised to the 9x plus 12 when you multiply those exponents together. Now we're talking about the exact same base on both sides. 1/2 raised to some power, 1/2 raised to some power, and these two expressions are equal to each other. So what must be true about their powers? They must be equal also, and that's that one-to-one property again. So this is not canceling out the 2 1/2s because that would be totally illegal. This is just recognizing that the powers have to be equal. And you get a nice linear equation. Add 4x to the other side, you get 13x. subtract 12, you get negative 22. So x is equal to negative 22 over 13. Some ugly number. Is it the answer? Last time we ended up with a negative answer, I got really worried because you can't take the log of a negative number. So, is this the answer to this problem? The answer is yes. This is not a log. This is an exponential. The graph of an exponential crawls along the x-axis and goes this way. So what's its domain? Well, the domain is anything. Anything you want it to be. Negative infinity to positive infinity. So this is the answer to an exponential. So exponentials, you don't have to be careful with their solutions. Logarithms, you do. Logarithms have to be logs of positive numbers. All right. How much harder can we do? We did that one. Have we done this one? I don't remember. Let's try this one. Log of 2x plus 5 is equal to 3. We want to solve for x. Now, how do I solve for x? Do I divide by log? Please don't. And please don't distribute log either. It's a function. It is not a number. Frank. Remember Frank? Frank don't do that. So if I want to get rid of the logarithm and I don't like working with it, what can I do to this expression? Change it to an exponential. What's the base of this logarithm? I didn't write one. It's automatically 10. So the base is 10. And if I'm going to change it to an exponential, it becomes 10 as the base. What's the power? 3. And it must be equal to what's left over? 2x plus 5. This trick of changing a logarithm to an exponential and vice versa, you need to know that one inside out, upside down. It'll save you on 90% of solving equations. How do I solve this equation? Well, 10 cubed is 1,000 is equal to 2x plus 5. Subtract 5 from both sides and you're going to get 2x is equal to 995, and then divide both sides by 2. And you get 995 divided by 2 is your solution. Does it work? Now remember, this is a logarithmic equation. Does it work? Now, all you have to check is, does it give you a negative answer? And the answer is no, it doesn't. So therefore, that's our solution. We can use that one. So generally after the first step, you either get a nice little linear equation, or you get something horrible. Hint, hint, horrible is coming. Where's horrible? That's horrible. Log base 2 of x plus 6 plus log base 2 of x minus 3 is equal to 2. Now a lot of these techniques kind of overlap, but some of them become easy and some of them become hard. The one that I did similar to this earlier had 3 logarithms in it. I combined 2 of them and then I got a log equal a log. This one is not so easy to do that way. There is a way of forcing the issue, but I'm not going to force the issue on this one. So since you have a log, and just a plain old number, what can I do to the left-hand side to make it look a little bit better? Well, you're going to change the addition between the logarithms to a multiplication between the factors and write it as a single log. So you write log once. What are the 2 factors that get multiplied then? X plus 6 and x minus 3. And this whole thing is equal to 2. Don't put log of 2. It's just plain old 2. All right. I want to solve for x. Problem, it's inside the logarithm. So how do I get it outside the logarithm? Divide by log? Heck no. Just imagine that the log isn't there completely and just erase it? No, not really. So how did I deal with the other one that was a log of something equals a number? Change it to an exponential form. So, do a little conversion on it. What's the base? 2. So write it rather large. 2. Raised to what power? 2. This 2 over here is equal to what's left? Well, x plus 6 and x minus 3, better known as x squared plus 3x minus 18. Since you have 2 factors, you better expand it out and see what's happening. Compared to the last one we did, this one's not so nice. The last one was linear. This one is quadratic. Yay! So 2 squared is? And then what do I want to do that for? Leave it. And I want to plop it on the other side. Get it equal to 0. Subtract both sides by 4. I think that's 22, yeah. And try to solve this equation. Let's try factoring. Factors of 22, then subtract up to 3. 11 and 2, I don't think they're going to subtract up to 3. What's the other option? Quadratic formula. This is a quadratic equation. Formula. So you're going to get x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Lots of holes to put numbers in. Alright, what's a? I'm sorry, what's b? 3, so that goes here and here. A is 1. So you get 1 and negative 22 is c. Don't forget the negative sign, otherwise it throws this whole answer off. All over 2 times a, which is 1. And then simplify this as much as possible. Oh, let's see, that's 9. That's 88. 88 plus 9 is 97. So this is x is equal to negative 3 plus or minus the square root of, what did I just say, 97? 97 all over 2. All right, I need the 2 decimal answers because I have no idea what that's equal to. I can find out though, but it's the old-fashioned way. Shirley forgot her calculator. Negative 3 plus the square root of 97 all divided by 2. So one of the answers is what, 3.4? 3.4-ish. The other one is, change it to minus, divide by 2. Negative, that can't be right. Oh, I guess it is. Negative 6.4. Negative 6.4. Negative 3 minus the square root of 97 divided by 2. Okay. Are those my answers to this problem?
Not the negative.
Why? No, that's not why. Just because you have a negative answer doesn't mean it's not an answer. I'll give you an example. If one of my terms was log of 2 minus x, and I got answers that were x equals 3 and x equals negative 1, which one's the answer? Negative 1. Because when you plug it in, 2 minus a negative 1 is a positive number. 3 plugged in would make it a negative number. So the negative answer works fine for that one. So you got to be careful. It's not always the negative answer. It's what makes the logs negative. So when I plug in negative 6.4, it doesn't work because when I put it in the first one, it becomes log of negative 0.4. And it's a log of a negative number, so he can't work. Does 3.4 cause the same problem? Well, thank God no, because 3.4 minus 3 is 0.4. The other one will be positive anyways. So the answer to this problem is 3.4. Only answer to this problem is 3.4. The other one becomes erroneous. Okay. Remember quadratic form way back when? E to the 2x minus 6e to the x plus 9 is equal to 0. A lot of these types of equations, they have a first step that you have to take care of using logs and exponentials, but generally after you do that, you go to regular old quadratics or regular old linear, and you solve it the old way. So I'm more interested in how you start the problems rather than how you finish most of them, except for this one. This one, you're going to start it like you normally did way back when in chapter 2, I think it was. And then at the end, it gets a little strange. So we have to be a little cautious of this one. This looks like a quadratic equation, but it looks quite weird. It's much different than what you're used to. But it still works with that quadratic form. You take the middle variable thing, the middle function, in this case e to the x, not just the x. You can't take the power. It has to be the middle function, so e to the x. And you say u is equal to e to the x. Remember this u substitution type thing. Then I take that equation and I square both sides. I'm going to write it off to the side here. You're going to get u squared is equal to, what's e to the x squared? Take a guess. If this is going to work, it better be the first term, which is e to the 2x. So let's make sure that works. E to the x squared. What do you do with the powers? E to a power raised to a power. What do you do with the two powers? You multiply. What's x times 2? 2x. So over here you get e to the 2x. It just looks a little strange the way it's written. Alright? Do your substitution. Replace e to the x with u, e to the 2x with u squared. And you get u squared minus 6u plus 9 is equal to 0. And now it looks like a normal, everyday quadratic equation. Yeah, almost said formula. Quadratic equation. And then factor it. Factors the 9 that add up to 6. Oh, this is nice and easy. Darn it. It's what is it? Negative 3 and negative 3. It's a perfect square one. All right, so we get u is equal to 3. I'm going to have to make up another one. This one's boring. I want 2 answers, not just 1. Now, u is equal to 3 is perfectly fine for solving the green quadratic equation, but it is not fine for solving the black exponential equation. So how do I go back to the black equation's solution? Well, what's u equal to? 3. U is equal to 3 here, but what was the substitution I used for u? E to the x. Bring him back to life down here and go e to the x must be equal to 3. How do you solve that little equation? Stare at it. Okay. I need to bring the x down. That's your focus. That x is up high, I need to bring it down low. Not down low underneath a fraction, just down low where all the other normal variables are. So what's the only thing that brings exponents down? Well, there are 2 things. You can log both sides. What's the other one? You can change an exponential into a... Okay, earlier we were taking logarithms and changing them into exponentials. You can also take an exponential and change it into a logarithm. You can change that into a logarithm. No. You said log both sides. Didn't you? Well, then I assumed you said log both sides. So either choice 1, ln both sides. I find this a little bit longer, but it's systematic with some of the other solving of equations. So you ln this side, e to the x, ln the other side, 3. What's ln of e to the x? ln e to the x. ln of e to the x.
It's big.
It's just x, right? Because these two are inverse functions and they go poof, and you're left with x. So you get x equals ln of 3. Now the reason I don't like that is people forget that ln and e are inverse functions. So the other thing you do is pull the x out front. ln of e, you can type it in your calculator, it'll give you an answer of 1, and then you get x times 1. The preferred way of doing it is just change it into an exponential or a logarithm. So this becomes log, what's the base? What's the base of my exponential? E. So you go log base e of 3 is equal to x. Log base e of the other side is equal to the power. Log is answering what power do you have to raise e to. Now, log base e is better known as, what nice little symbolism. Log base e has a special little button on your calculator. It's definitely not log because log has a base of 10. It's the other one. What's the other one? ln. Log base e is the same thing as ln. And you get the same answer, x equals ln of 3, x equals ln of 3. Depending on how you want to do it. So you either A, log both sides, simplify your expression, or B, change the exponential into a logarithm. How about this one? I'll just make it up. E to the 2x plus 5 e to the x minus 6 is equal to 0. Yeah. Now, if you do this a few times, you can start seeing how to factor it right from this form, but it'll take you a few times of doing it. So first up, let u equal, what's u in this case? E to the x. And then square it, so you get u squared is equal to? E to the 2x. And then do your substitution. So I'm going to do this one rather quick because it's basically the same as the other one, just a different ending. So you get u squared plus 5u minus 6 is equal to 0. And then factor. Factors of 6 is subtracted to 5.
U minus 1.
What are which ones?
U minus 1 and U plus 6.
U minus 1, u plus 6. And this is equal to 0. Alright. So out of this we're going to get u equal 1 and u equals negative 6 after setting both of the factors equal to 0. But we're not trying to solve for u, we're trying to solve for the variable of their x. So that's when you go back to your first substitution and you bring it back to life. Replace u with replace u with, I want to come back to the variable x. The solution, but I don't know what it is according to x. So it becomes e to the x is equal to 1. Now this one you shouldn't even have to solve. When is e to the x equal to 1? When x is 0. It's the only way. Or you can change it into a logarithm and you get ln, that's log base e, of the other side, which is 1, is equal to x. And ln of 1 is guaranteed to be, what power do you raise e to get a power of 1? Well, 0. Either way works perfectly fine. All right, let's look at the other side. This one becomes e to the x is equal to negative 6. This is where e gets funny. You have to kind of remember what the graph looks like. The graph of e to the x crawls along the x-axis, hits this point, 0, 1, and then shoots off and grows exponentially. So what's true about this graph at all times? Does it ever get below the x-axis? No. So the values that it generates are always going to be positive. So e to the x can never ever equal -6. Now the guarantee on that is if we change it into a logarithmic expression, it becomes ln of -6 is equal to x. And then you get this, you're taking a log of a negative number, that doesn't work. So this doesn't give us a solution, so the only answer is 0. Pretty cool, huh?